Welcome to today's webinar, announcing Amazon Rekognition, Deep Learning-Based Image Analysis. Our presenter today is David Pearson. David is Principal Tech Business Developer for Amazon Cloud Drive. Today with us, we also have Anil Bhandari and Shailu Verma. They will serve as our webinar moderators and will engage with you and answer your questions throughout the presentation while David presents. David, welcome. The floor is now yours.
Thanks very much, and welcome everybody. This is an introduction to our newly announced service. We announced Rekognition at our recent reInvent conference, and so what I'm doing today is bringing to you the same content that we produced in a breakout session. So it's more broadly available, and you can understand a little bit about what goes on underneath the covers of Rekognition, how the use cases make sense for this sort of technology, and just the core features and functions of the product. I think the base understanding really is important, is that images these days are not just a consumer affectation. We obviously are fully aware of the volume of consumer photos that exist on both on the social media as well as storage sites and so on. But across different industries, media has been a driver of their content for many years. And as we merge further into more cloud-connected industries and in cloud-influenced industries, different organizations are looking at different ways to get value out of their images. And so this is really creating an explosion almost of image content and a strong desire to make sense of it. And that's really what we're trying to address today. From the consumer side, if we look at the explosive growth on just consumer images, the number of photos that will be taken over 1.2 trillion in 2017 alone, according to the forecast here from Inference. But if we look at existing deployment of images and the storage of images currently in S3, we did this analysis just to get a sense of how many images and what sort of shape is the growth for the storage of images in Amazon S3. So bear in mind the 2016 number is actually a few weeks out of date, so that's already substantially higher than that. But you can see the exponential curve there kicking in, and that's no surprise. That's the way storage is in general. Images follow that trend as well. The difference being, of course, it's easier to understand what's in a file because there's text there. Images have always been this black box, very, very difficult to understand without the human eye. And this is really where we talk about Amazon Rekognition as a way to really enable human-based recognition that's always been done previously by humans into the machine learning space. So it's a deep learning-based image recognition service. It understands what's in images, allows you to search, verify, and organize millions of images. So there are four main components to Rekognition. Object and scene detection, which looks at the contents of an image and then produces labels and a confidence score. Facial analysis, which reviews images of faces and then tells you a little bit about the faces in the image. Anonymous features, things like what are the eyes doing? Are they open? Are they closed? Is the person smiling? We talk about sentiment as well, and we'll go through each of these. Face comparison is a way of scoring the similarity between faces in two images, a reference image and a comparison image. And facial recognition, the ability to understand, identify people in images from their faces. So let's jump into a bit about the APIs as well. For object and scene detection, okay, what we're doing here is looking for elements, factors in the image itself, and how this is submitted to the Rekognition API is by calling detect labels. So the image comes in to detect labels, and what comes out is JSON. So in this case, we've taken a snippet of the output, where you can see here the output is structured in a way that gives you the confidence score as well as the name or the name of the label. Now these are presented in descending order of confidence. Now these are requests that you can also tweak. We do have a min confidence level which enables you to look at, you fine-tune that. I think we do emit anything above a 50% confidence, but you could move that to 70% if you wanted a much higher rating. Now the confidence score refers to the confidence that the model, the deep learning model, recognizes that object. It may not necessarily be the main object and the confidence that that is the main object in the image, but it's how clearly we recognize it, the confidence that we recognize that object in the image. And so if we look at a few examples of this, an indoor example here where we're detecting, when we talk about objects and scenes, objects are self-explanatory. We see here flowers, coffee table, chair. But also we have scenes like living room. We understand that. Or concepts like indoors. We recognize that this is an indoor scene. And so objects, scenes, and even concepts are what is produced by the Detect Labels API. An outdoor scene, we recognize it as, with the factors there, you can see villa, maple, the type of tree, which is pretty impressive. This is a good example of the case where some elements are very distinctly recognizable, like a maple tree. They will also help populate other tags, like tree itself, as we can see there. And we also have plant garden, swimming pool. So this is an outdoor scene that is probably typical of any backyard, depending whether you have a pool or not. Certainly one in which you have the ability to, by submitting an image like this, is to understand what's in that image, form structured data as output, and then use that data to act upon that. Typically what you would build with this is you could build a number of things depending on the sort of industry you're in. What we see a lot of as a generic scenario is the ability to turn these labels, convert them into search tags. So building a search engine, for example, photo sharing apps, using a smart search engine so that the users, the consumer users, looking through their photos can quickly find the memories, such as weddings, hikes, sunsets, and so on. Real estate, vacation rental markets, travel sites also find this extremely interesting from the perspective of enabling their users, often with user-generated content, which is very hard to label at scale. It's hard to tag at scale because of the scale. So by automatically labeling those and then providing them as a search engine, it enables customers to get very fine-grained on the things that are important to them. It's very hard to predict what's important to a consumer, but as they're looking, they can say, I need a fireplace, a kitchen, and a swimming pool. Then that can be the search criteria, and the filtering can produce those places. So that's what we talk about when we say a smart search. The more data you know about the images, the more content you can extract, the better the quality of your search experience. So if we look at what this looks like as a, we'll use that real estate one as an example, this is where you can build a dynamic search index. So with recognition at the back end, doing the actual retrieval of understanding the image and then providing the labels back, what does it look like at the front end? A mobile app, for example, in this case, is capturing the image itself and storing it straight into S3. That's always a very strong pattern, by the way. One, to get it off the device and put it into a persistent, durable store, S3, it's hard to beat 11 nines of durability, but also to decouple the capture of the image from the subsequent processing. In this case, we're understanding the contents of the image and then converting those contents into an Elasticsearch, a search index, such that the application users can now search for that image by the contents of it. So in this case, we've set up a Lambda trigger. Now, when we launched with Lambda as a blueprint. So if you just go to the Lambda page and create a new function, you'll see you can type recognition to filter on what we call blueprints, which are templates. And so this gives you 95% of what you need to build this interaction very, very quickly, at about 5 minutes of coding. Now, what essentially you'll be doing is once you associate that trigger with an S3 bucket and probably on creation of new objects. So when a new image is put into that bucket, the Lambda function will fire based on that trigger. It will then call recognition, passing the image to it, actually passing the URL, because recognition accepts both URLs and raw images as input. Passing the S3 URL, the recognition will return the JSON as we saw previously, and then Lambda will then pass that JSON to Elasticsearch for indexing. You can also weight that that using the confidence score, which is a pretty exciting way to ensure that the more confident searches, the more confident items in the search bubble to the top, producing a much better search experience. Now, with Lambda going on, this can happen literally in a handful or even a few seconds after the upload of the photo exists. So it's a very fast function. It's dynamic. It's self-constructing in that the search index is constantly being updated as images flow into S3. So the effort to maintain this is effectively zero once it's been built. The next API is a facial analysis, the ability to detect face and key facial characteristics from images of faces. So as an example here, we look at, it does two things. One, we extract all the faces in the image and we look at those individually. Then we emit the JSON. So in this case, we've described one of the faces by the bounding box. That's how you understand which face is being referred to in the subsequent JSON text. So we've overlaid the face there so you know which one the JSON refers to. So in this case, that bounding box identifies that first face with a high confidence that it is a face, which is also important because some faces are occluded or turned away. So while we may do analysis on it, our confidence that we are actually recognizing a face might be degraded based on the quality of the image itself. But with a high quality image, we get very high quality analysis of the contents of that image. For example, we're looking at emotions here. Very high confidence of a happy face and then much lower confidence of other things we're detecting. So Rekognition detects, I think it's 7 different types of emotion in the face, whatever's expressed on the face of the image that's being processed. Then other attributes like eyeglasses, are the eyes open, the gender, and so on. So there are a number of things being detected here, including the facial landmarks. So if we look at the type of things we're analyzing with facial analysis, it includes demographic data, sentiment or emotion, facial landmarks, which is where things are in the image, where are the eyes, the nose, the mouth, and other general attributes, as well as image quality. So in this case, we have a high confidence of a mustache and a fairly high confidence of a beard. We have a high confidence that this individual is smiling, he is male, and he's expressing a happy emotion. And as I mentioned, there's many more things that we haven't shown on the screen, including the location of eyes, nose, mouth, and 25 altogether landscapes about the face. How to use Rekognition facial analysis. This is an interesting approach that different customers are adopting here. So it could be as simple as saying best photo. These days we're taking bursts of photos rather than individual photos because it's all digital. So it's very easy then to compare a series of photos and say this one scores the highest. And it could be a case of smiling with the eyes open. The pose could be directly towards the camera. We're also expressing or emitting the data for the pose, as in roll, yaw, and pitch. So best photo is actually a nice simple use case. It could be also as simple as saying there's the face, don't crop it if you have to do cropping, or don't put an ad over that face. That's always a bad thing to do in a facial image where you could put the face, say if the example we have there, you could put the ad below the face or to the bottom right and still have a good image of the individual as well as have the ad shown. When it cuts over the face, it's not a great experience. Social and particularly online dating applications, all the attributes possible known to a face are useful for the dating engine or the match engine really. The more you understand, even down to facial hair, things like that, it can be very interesting for different customers in ways of matching people. Retail business is an interesting one. I'm going to talk about this a little bit more, in fact the next two. Talking about demographic analysis and sentiment of in-store customers. That plus the next one, the ad tech services, where you could make that whole cycle a whole lot more dynamic and deliver personalized content. Very interesting. So when we talk about the first one there, retail, in-store and online, in fact anywhere, if you imagine it, we have customers in the store, we have images of them in the store. What we can do is understand a little bit about them, anonymously of course, as well as a little bit about the sentiment they're expressing. So we have a happy smiling female, we have a happy male with no facial hair. On the right-hand side, we have an unhappy female who's not wearing eyeglasses. Now, depending on the product you're in, depending on the analysis the data you're trying to understand, this could be super interesting information. How to put that together is really a very simple case of just capturing the data, capturing the images, storing them in S3, and then periodically uploading them to Redshift to do this analytics. The value of Redshift, of course, is it can process masses of data very quickly. So by using an in-store camera and having sort of a constant feed going in there, you get a really good sense of, it's a touchless way of capturing anonymous data about your customers and then doing some analytics through a tool like Amazon QuickSight in order to produce marketing reports to understand, say, demographic, or could be service reports for sentiment analysis and so on. So this is a way where you could say, look, we've launched a campaign targeted at this sort of audience, and let's see the effectiveness of that in-store. Have we seen an uptick in that, say, demographic profile? We talk a little bit more about real-time. This is a really interesting scenario where you could personalize content based on the individual in the image itself. So, for example, this gentleman would see an ad for a razor, the woman would see an ad for a pair of glasses. And the reason being, of course, we detected the attributes on each of their faces such that we could recommend that sort of ad. So what that looks like under the covers is when the image of the individual is collected, then detect faces is called from Amazon Rekognition. The demographic and sentiment attributes are returned and then stored in DynamoDB, and then by those demographics themselves trigger a lookup, a very fast lookup to determine what ad to show. And so that ad is returned back from that call to DynamoDB. The actual ad itself is retrieved from S3 and then displayed in this case, we're talking about like a dynamic billboard. But that's how you could turn this around in a typical way that ad tech use cases are provided. You could turn this around in a matter of tens of milliseconds, that sort of approach. Now on the back end, what you've got here is also the reason we're storing the metadata is then we log it into Redshift so we can run demographic profile analysis on that. So we can, over time, as we collect more information, we can target better ads. And so with the output of that decoupled process, we then upload the demographic profiles back into DynamoDB, and that services the real-time use case by telling the application which ads to display as a result of recognizing a specific demographic. And like as an extension to this, you might not even just use detect faces, you might use detect labels and ascertain that and recognize a tie and a suit for this individual. And you may show a different ad with that extra information. All this is made possible by, again, looking into the image, understanding what's there, and then enabling activity based upon that. The third part of the API is compare faces. Now with compare faces, it's really about verifying the similarity between two faces. So in this case, we're looking at two different images of an individual, calling compare faces, and then you can see the output there. We are comparing the first image to the second. In the first image, the source image face, you see that down the bottom, is identified. When there are multiple images, we're detecting the largest one, the most prevalent face in the image, and we're comparing that to every face in the comparison image. So in this case, we have two faces there. And so we have a similarity of 96 for the first face, which is obviously the same gentleman, and the young lady has a similarity with that gentleman of 0, which is exactly what you'd expect. So what we're providing here is the bounding box, so again you know which face is being compared and the similarity of that face to the source image. How that looks in a real-world scenario, you can identify people who look similar but may not be the same person. In this case, it's definitely the same person. She's obviously got a very different look, and we've emitted a similarity score of 94%. And we'll see these as I'm going to jump to a brief demo a little bit later in the presentation. So how would you use face comparison, recognition space comparison? This is a very interesting area where you could build it directly into like a hardware, where you make these firmware updates that make calls to the service. Remember, this is a stateless service, so what it means is two images are sent to the service to face comparison, and then the JSON is returned. Nothing is stored, nothing is preserved. It's literally just a processing exchange. And so this could be built directly into hardware where cameras and visual data is collected. Public safety is an interesting one. At reInvent we had a great presentation and a live demonstration by Motorola where they were using body cam data live to locate a missing person, a missing child. For example, in that case there was a missing adult because there was the presenter's accomplice on stage, but it was very fast recognition where once the comparison score was high enough, it quickly then alerted the officer that there was a probability of a missing person found. VIP access, if you imagine that providing a quick verification score for VIPs who opt into a superior experience, maybe buy their way in, and then you can make the hospitality business could make that a very seamless process without constantly having to re-identify the person. They could make that very, very seamless as they move through the facilities. Online exams can also register a user and then verify against that person, making sure that the person taking the test is the person who registered for the test. So this looks at the back end very simple. Images are captured, the authenticated user. If we think about like a badge scan scenario, like the gentleman going through the turnstile, for the authenticated user, so we know who it is. And what we're doing, we're trying to verify that user and make sure that they haven't stolen or borrowed a badge. So in this scenario, the application is accepting both images, the image plus the authentication token. Using the authentication token, it looks up the image of the user that is identified, as well as passing the live image plus that URL back to Rekognition. And so the compare faces is called, the similarity score comes back, and the green light goes off. This is a great way to augment security using existing infrastructure, camera infrastructure, so that security guards, for example, can get a very fast alert on a potential badge violation. The final API is really about facial recognition, and it's actually built on a series of concepts in Rekognition. In fact, there are 8 APIs around this, and they really fall into 3 categories. Collections, faces, and search. So a collection is it's a storage of face vectors. We're not storing images. All the previous 3 use cases scenarios are calling APIs that are completely stateless. In this case, we are storing things, but what happens is that what we call the feature vector is extracted from the face, and then that is stored in the collection. Collections are entirely owned by the account itself. They're not shared. They're not even shared outside of the calls to that account, and they're only accessible through the API. Now, how you populate a collection is using index spaces. Index spaces allows you to convert images into individual face vectors inside the collection, identified by a unique face ID. And then once that collection is built, at least a few in that is built, you can have a lot, then the search options come in, and you can search face by image by submitting an image that will then enable you to identify close matches. So if we break down the flow here a little bit on the indexing side, with an image as input, we are extracting 3 different faces from that image. We're transforming each of those into a unique vector and attributing each with a unique face ID. Now, the face ID is essentially a hash of a number of items, including the image and the face crop itself and the collection name and the account. So it's essentially a GUID for your for each individual face. So once that's identified and emitted as the response to this index face operation, and then it's stored in the collection. And you see that happening, 1 image in, 3 faces out, and then the collection is populated. On the other side is now we want to search against the collection of stored faces. We call search face by image, using an image. It could be a face crop or a full image. If it's a full image with multiple faces, again, we'll take the most prominent face. So we do recommend face crops to make sure that the precise image is the one being searched for. So we can do that in two ways. You can search by face by image, where the image comes in, or if you want to search within the collection itself using an existing Face ID that you're aware of, then you can use that as input, and that's called search faces. And so what happens here is the high dimensional space search. This is the dimensions we break the features into, a number of feature vectors, and against that, or those multidimensional search criteria, or that space, we're searching for close matches on that. And so what we're doing, we're comparing a lot of different points to give a high confidence that we have a match. And then what happens is that output of that is the JSON is emitted, saying here are the faces, here are the similarity scores, and the confidence that we have a face. So it conceptually looks more like this, where we have an image in against a collection of faces in an image, and then we can identify the individual in the input image within the collection itself. So these will come out in, again, descending order of similarity, so that we anything above 80, 90% is a very, very high confidence that it's the same person. If there are, again, the quality of the image heavily influences the ability to recognize that. So if there are low quality images or the face is turned slightly or significantly, we may have a lower score. That may be, you want to surface that as a verification step. So how to use facial recognition? I mean, there's a lot of ways. The consumer photo apps are a very obvious choice and very popular. So like family photo sharing apps, where once the users have tagged or named the faces in their collection, their own private set of photos, then subsequent photos are named as they come in. So you identify your parents, your sisters, your brothers, and so on, your kids. As more photos flow in, they automatically get tagged with those names, assuming, again, a high confidence. And over the years, that actually works out quite well. As you see people's face evolve over the years, and they're still recognized going forward. Now, for organizations that have large archives, this is a really interesting scenario, because if you imagine all the stored footage of visual content, which is, to date, up until very recently, it's been impossible to understand what's in that content without having a human present. And that's just a lot of footage to go through. And so this now offers a case where mechanically, systematically, you could understand and catalog and classify and recognize people in enormous volumes of image libraries that have been stored over the decades. In terms of security, there's a lot of security potential here as well. Secure campuses, workplaces use face. Again, this is anonymous, and I'll explain why that is. We're just matching a face to a face, so really a feature vector to a feature vector, and then putting out the similarity score. We'll show you in the next slide how we would build that into an architecture where you would do actual person identification. But there are a lot of applications for this and implications for public safety and security. So if we look at how we would index faces into a collection in a way that we would, in this case, we want to name the young lady there. You want to name the individual in the image itself. So what happens is that you'd have an application index. So essentially what this is doing is capturing frames from a camera and then storing it in S3. Again, the Lambda function would trigger, and it would call index faces, and it would then store the output of the index face call, which is a unique face ID, into an application table. We're calling it person details here, an application table that stores the face ID next to the real name of the person. And so when you have the application indexer, if you know the name of the person, you would store that and then associate that with the face ID, and then subsequently you can do recognition against that. And what happens after that, if you load images where you don't know the name of the person, you could convert that into a search and look them up, and if you get a high confidence, then you could then go and name that person in the personal details page. So by naming a person once or twice, if there's like very high variation between the types of image of an individual, you may need to name a few images. But generally once or twice is enough to do subsequent recognition. And then with that you could do a search where the reference image comes in, say, oh, who is this person? We look them up in the collection and get a high confidence score. When we have a high confidence score, we put a name to that, then we can go and update the person details table with the new Face ID of the new image with the name that we've extracted from the search. Or if you don't want to do if you don't want to index the face at all at the same time, then you could just do a kind of a remote search where we just say of the faces we've collected. For example, it could be a missing persons database. How about this image? Is this person in that database? Nothing is stored in that case. It's simply done a comparison against face vectors that are stored, and then confidence is emitted. The similarity score is returned, and if it's a high confidence, a high similarity score, then you probably have a close match with the missing person. So if we look under the hood of recognition, there's a few important functions here that are going on. Firstly, recognition is a deep learning based system. So the deep learning underpinnings imply a whole lot of stuff that's going on. What happens is this, is the image comes in and then it's basically looked at layer by layer. It's a multi-layered system which what it does is they look for different attributes in the image. For example, the edges, trying to find the edges, or looking for clusters of contrast in the image. And each of these layers has been trained to say, based on the edges, it looks like this. Based on the clusters of contrast, it looks like this, and so on. So these multiple layers are analyzed. It's like each of these is looking at a different part in the image, and then there's a fully connected layer where all of this is consolidated back. And based on the consolidation, the contents of the image get classified. So here we have the classifier emitting the examples of the labels that were detected: Labrador, dog, beach, and outdoors. And then going further on that is the probability or the confidence that label is present, that object is actually a Labrador in the screen. So in this case you would see things like a Labrador and a dog, but very high confidence there. But if you had confusion, or potential confusion between two dog breeds, which is something a human would have as well, then the Labrador score may be a little lower, but the dog score would be higher, because it might be a Labrador or say a Golden Retriever, and they may be, say, 60% confidence, but either way it's a dog, and dogs are like a 90% confidence. So these are the ways we also introduce a kind of a hierarchical relationship within our knowledge graph, where subcategories of labels like dog breed actually contribute to other labels and give them a boost in confidence, like the type of dog, or like the label dog, I mean. The training process is an interesting one, where it's really an iterative approach where data is sourced, it's annotated, in other words it's labeled, it's validated. So what that means is this: we take images to build training data. We have, and I'll jump to the next slide shortly, which introduces our human-assisted training process. Humans are a critical part of deep learning systems, and the building an efficient pipeline is really a lot about doing very efficient workforce management and integrating that with automated processes. And the humans provide a good visual annotation, and what they're doing, they're building that, what we call ground truth data, so that we can use that data to then use the machine to make those decisions going forward. And of course, annotations may be incorrect from humans, so we have a validation process to verify that when they are correct. So on a broader scale, I'm not going to walk through this in too much detail, but the training process kind of looks like this. And this is important because there are an infinite number of labels that could be provided. We have thousands of labels at launch with Amazon Rekognition, and we're adding to this every single day. And now what our approach is quite simple, is to look for customer feedback on what are the important labels and categories of images to them, and then we'll use that as prioritization for populating this process. In the background, we're also always consistently enriching this by sourcing our own sourcing requirements outside of customer requests as well, in the areas of kind of continually improving quality, as well as extracting information about new areas that we're keen to explore. So you see the human-aided active learning system as part of this, and that's really where they're providing that annotation, which results in a labeled image, and that goes into our ground truth model. And from that model, the inference is made such that once it's published, then subsequent images that come in are recognized against that model that's built around that ground truth data. So very complex. I think the important point of this is that this is a part of the service. It's not something you need to build yourself. If you're doing your own deep learning system, then this is actually a very important thing to understand, because any push towards quality will require a version of this process. Maybe a bit simpler than this, but certainly the core parts are there, which is unique human-aided systems, verification steps, and the ability to train a model based on verifiable and verified ground truth data. The data pipeline is automated, as I mentioned. It's extremely simple for what it is. It does a lot. What we've done, we've broken it out into very distinct steps so that each step has a very distinct function and purpose, and we can therefore measure the quality of each of those stages in a very high level of detail. And it's also very fast. We're currently turning around labels in the order of a few weeks, but that's really because we've just launched this and are ramping this. We expect to get that down to days in the near future. When we think about the human element, the human workforce part of the process, it's elastic. They are our resources that we've trained, so they're highly trusted resources. We've expanded on a global workforce and therefore fully available. So we have basically a around-the-clock process operating that interacts between the automated processes and the human processes. So let me jump to a quick demo. I just want to show a few of the highlights here of Rekognition. You can see my screen there. This is inside the console, and what we've done, we've put the demonstration inside the console to enable AWS users to quickly. You can do this yourself. You just log into your console and go to the AI services section and click on Rekognition, and you come up to this area. And so the idea is very simple. At this stage, we're showing 3 of the APIs, the first 3 I mentioned, which is object and scene detection, facial analysis, and face comparison. These are all stateless calls, so nothing is stored, nothing is contained. It's really image or images come in, they get processed, and then JSON comes out. So the interface you see here is really just a visual representation of the content as it flows through. So having submitted this image, we can see here the output here, and this is a limited list. I'll show you the full list later. What I want to do is get to what the request looks like. So if you have your own images, you can upload them into here and see what a request looks like to the service, and then what the response looks like from the service. As you can see, it's a lot bigger than we're showing on the screen. If we show more, you can see all the items we've detected. Anything above a 50% confidence in that image is shown there, right down to the bumper of the car. So this is again, if you think about this, the opposite way is actually how it's used. We're putting in images to capture the labels, but actually the use of this is really by building that search index such that you could search for city, downtown, metropolis, high-rise, and then this image would be one of those that are presented from that search. When we look at facial analysis, the ability to understand what's in the face. Let's have a look a little more here. Confidence that it is a face, female, smiling, happy, mouth is open, eyes are open, wearing glasses, wearing sunglasses. The multi-face scenario is also important. We're highlighting then the face in question and showing it again above the metrics, but we can look at any one of these as well. So in this case, we're detecting, and if you're in the business of selling razors, it might be material that this gentleman has a mustache and a beard. Wearing eyeglasses, not wearing eyeglasses. Again, it depends on the industry you're in, the scenario. The one we find a lot of interest in is really to say there's a male. So we're extracting some demographic data, which can be then further analyzed with very low collection effort, but also then the sentiment, which might represent a support experience in a store. In face comparison, it's really about verifying two images. Here we've just got one young lady and then in a group of three, and you can see the similarity scores between that source image, the reference face, and the comparison face. Even though she's at a quite significant different angle there, we still have a very high recognition of her face there, high similarity score. And even though this third young lady here, her face is partially obscured, we have a very high confidence that it is her. So this is a great way of sort of demonstrating that what we're doing with the faces here, turning them to a very high dimension feature vector, and then comparing the elements of that vector together, so we get a much higher kind of hit, a confidence score on the similarity. Okay, let's just go back to the slides, and I'll just finish up, and then we're going to pause for Q&A. So Rekognition is a fully managed service. It is a global platform that is really accessible through the API, and that's really all you need to know. In terms of deep learning, you don't have to be a deep learning expert, which is a significant amount of knowledge and experience to actually be required to run a system like this. It's very difficult to do, and so we've simplified that incredibly, specifically to make this much more appealing to as many different use cases as possible. It makes it very easy to integrate. We've also integrated with other services like Poly and Lex, if you are familiar with those announcements. Lex is the technology that drives Amazon Alexa in terms of the conversational interface. Poly is a text-to-speech, very natural language a service that enables you to convert text into very, very lifelike speech, but also integrations in with S3 and Lambda to make sure that near real-time image processing or batch processing against large stores of images in S3 is easily accomplished. Proven scalability. This service has been running in production prior to our launch, in fact, within Amazon, where we've processed billions of images every day. So we've already internally proven the scalability beyond reasonable limits. There's no doubt there. It's operating at a very high scale and continues to grow as people come on board. It's extremely secure as well. Besides all the goodness of AWS in terms of security and protection, we've taken additional steps in making sure, one, the API itself preserves a tremendous amount of security. There's no access to the back end. But also, it being stateless, there's really nothing that can it minimizes the potential for impact there. The stateful, the storage-related use case there, where we are storing feature vectors. We're not storing the images, we're doing the vectors, accessible again only through the API via the search function and other things like list faces and so on. But very, very secure down to the description of the Face ID and the uniqueness of that. So there's no ability to have confusion at that point. And we've aimed to get the price down, make it very competitive so that comparing it to, say, to build your own deep learning stacks, taking into account all the effort, the heavy lifting, it's an extremely attractive offering, and that's deliberate. So what is our pricing and what is the availability? Currently, so we are generally available. The service is available in 3 regions, 2 in the US and 1 in Europe, and the pricing is pay-as-you-go. So I'll show the pricing next. What's important at this stage about the pricing is for 5,000 images per month are free. So we have a very large free tier designed exactly so you can try this without paying a cent for it. And if you get through that free tier, then you'll see the prices are still very low. The first 1 million images every month costs you $1 per 1,000 image processed. And that number goes down to 40 cents per 1,000 images processed when you get over 100 million images processed per month. So in summary, a fully managed service designed specifically to be easy to use above all else. High quality, very easy to use, provides 4 main capabilities: object and scene detection, analysis of faces, comparison of faces, and then recognition. Integrated with the AWS and AI services, as mentioned, Amazon S3 and Lambda, Lex and Poly, and it's extremely scalable at a very low cost. If you want to get started with Rekognition, that's the URL. Visit Amazon.com. You can look in the products page in the console if you want to try that try the demo yourself. Under the AI services, you'll see Rekognition. But on the public web page, you'll see there as well more information about the service and the main capabilities. So with that, we're going to pause and take some questions.